Hello, it's Dr. Armand again, bringing you another exciting lecture on acids and bases. Today's lecture will be focused on three things. First will be how to determine if a salt solution is acidic, basic, or neutral, what cations are acidic, what cations are neutral, what anions are basic, what anions are neutral. Secondly, we'll be talking about the third type of acid-base theory, Lewis acid-base theory, which involves the transfer of electrons. And then finally, we'll be talking about how you can rank acids to determine which one is stronger than the other one. So on that note, sit back, relax, and let's get started. So I'd like to call this chapter 18, part 4 in this lecture series on acids and bases. And so when we're talking about salt solutions, there are three types of salt solutions. There are those salt solutions that, for example, are neutral solutions. So when you put these salt solutions in water, there's no change to the pH. Then there are salt solutions that give you basic solutions. So when you dissolve these in water, you get a basic solution, slightly basic pH. And then the third type are those that are acidic solutions. So they're slightly acidic. Now for salts that yield neutral solutions, and this is very important, the salt consists of an anion from a strong acid and a cation from a strong base. This yields a neutral solution because the ions do not react with water. And so what are the strong acids? These are the strong acids except sulfuric acid. So these are your strong acids. If you've forgotten, just to refresh, strong acids. We're talking about HCl, HBr, HI, HNO3, HClO4. So these are the common strong acids we're referring to. We're not referring to sulfuric acid because bisulfate ion is a little bit different. So with these, if you have a salt that contains a chloride, bromide, iodide, nitrate, or perchlorate anion, that anion is going to be neutral. It doesn't affect pH. Secondly, cations of strong bases. These are going to be your group 1 cations, so lithium down to francium. And then your heavier group 2 cations, calcium, strontium, barium as well. These are neutral cations. They don't affect pH. So what are some neutral solutions? So things like NaCl. Na is neutral. Cl is neutral. Let's see. BaNO3 Nitrate is neutral. Barium is neutral. So when you dissolve these compounds in water, they're going to be neutral. Strontium chloride, neutral. What else? Calcium iodide, neutral. And we'll give you one more. Let's see. Potassium perchlorate is neutral. So again, these contain a cation that is neutral and an anion that is neutral. Let me show you. So here the cation is neutral, sodium, and the anion is neutral. So if both your cation and anion are neutral, when you dissolve it in water, it's going to be a neutral solution. Barium is neutral, nitrate is neutral. When you dissolve it in water, it forms a neutral solution because those ions don't interact with water. They're neutral because they come from a strong acid and a strong base. So this is what makes up neutral solutions. Now, acidic solutions are two criteria that we're going to talk about. And so for acidic solutions, it's the cation that is responsible for the acidity. So you want an acidic cation. So if it's one of those cations we talked about on the previous slide, those are not acidic cations. And so a salt consisting of a cation of a weak base and the anion of a strong acid, these yield acidic solutions because the cation will interact with water. So what's a cation of a weak base? For example, is ammonium ion is a cation of a weak base. Also, for example, CH3 dimethyl amine is a cation, or dimethyl ammonium cation is a cation of a weak base. So those are cations of weak bases. Usually they're protonated amine compounds. Ammonium, the cation of ammonium, or excuse me, cation of ammonia, the cation of dimethyl amine, things like that. So those are cations of weak base. The next criteria for acidic is a salt consisting of a small, highly charged metal cation. And it includes an anion of a strong acid. Because what happens is the small, highly charged metal cation acts as a weak acid and reacts with the water. The anion does not. These are generally going to be your transition metals and post-transition metals. Post-transition metals like aluminum, gallium, tin, lead, etc. And what happens is when you have a small, highly charged cation, like iron, you put it in water, you form this hexa-aqua iron complex. And then what happens is it donates a proton and you get this resulting complex ion and you form hydronium ion. So it dissociates as like a weak acid. So what are examples of compounds that contain a cation of a weak base or a transition metal with an anion of a strong acid? So for example, ammonium chloride would be acidic. Ammonium nitrate would be acidic. Iron bromide would be acidic. So again, all of these contain acidic cations with neutral anions. Let's see. Zinc iodide would be slightly acidic. Aluminum chloride, slightly acidic. There's so many. Cobalt perchlorate, cobalt 3 perchlorate, slightly acidic. So all of these have in common, they have an acidic cation and a neutral anion, because the anion comes from a strong acid. So if your salt contains an acidic cation like ammonium or ammonium derivatives, or a transition metal or a post-transition metal, and an anion from a strong acid, then it's going to be an acidic solution. So cations are what give acidity to the solution, not anions. So your cation has to be acidic, your anion has to be neutral. Now it's the anion that's responsible for the basicity of a solution. So what you want is you want a solution that contains the anion of a weak acid. So you want a salt that has an anion of a weak acid. And I'll give you some examples of weak acids. I mean, where there's a whole slew of weak acids like HF, HNO2, HClO. All of these are weak acids. Let's see what else. H3PO4, H2CO3, etc. This is just some examples. So there's thousands of weak acids. Acetic acid, etc. So you want an anion of a weak acid in your salt and the cation of a strong base, because those are neutral. So if you have a cation of a strong base and an anion of a weak acid, it's going to give you a basic solution. So for example, if we have sodium acetate, sodium is neutral, acetate is weakly basic. It's going to react with the water to produce hydroxide ions. So other examples of weakly basic solutions could be things like potassium nitrite, sodium hypochlorite, strontium carbonate, sodium bicarbonate, barium fluoride, potassium acetate. So all of these are solutions that contain a basic anion and a neutral cation. So NO2 is basic, potassium is neutral. ClO is basic, sodium is neutral. CO3 is basic, strontium is neutral. Bicarbonate is basic, sodium is neutral. Fluoride is basic, barium is neutral. Acetate is basic, potassium is neutral. So if you have a basic anion and a neutral cation, it's going to be a basic solution. So that means the cation came from a strong base, the anion came from a weak acid. Now the obvious question here is what happens when you have a weakly acidic cation and a weakly basic anion. So if you have a salt like ammonium cyanide, ammonium is acidic, cyanide is basic. So then you have to look at the relative strength of the Ka of the acid and the Kb of the base. And whichever one is larger, then it's going to be, tell you what if it's going to be acidic or basic. So if the Ka of weak acid larger than Kb of weak base, it'll be acidic. If Ka of weak acid less than Kb of weak base, it'll be basic. And if in the rare occurrences, Ka of weak acid equals Kb of weak base, as you can imagine, it would be neutral. And so for ammonium cyanide, what you would have to do is in the back of the book, you would have to look up the Kb of ammonia. That's what's here. And then you take the Kw divided by the Kb of ammonia, you get the Ka of ammonium. Because the Ka of ammonium is not in the back of the book. The only thing in the back of the book are Kb's of amines. Now for cyanide, the KB of cyanide is not in the back of the book. You have to look up the KW, or excuse me, the Ka of hydrocyanic acid, and then Kw divided by Ka tells you the Kb of cyanide. The Kb of your anions are not going to be found in the back of the book. You have to take the Kw divided by the Ka of its corresponding weak acid. And since the Kb is larger than the Ka of ammonium, then cyanide is a stronger base than ammonium is an acid. Therefore, it's going to produce more hydroxide than hydronium, so the solution is basic. You only compare Kb when you have a weakly acidic proton and a weakly basic anion. So your cation is weakly acidic, your anion is weakly basic. That's when you're going to have to compare the Ka and Kb. If one is neutral and the other one is acidic or basic, it's straightforward. And then there are some salts that can behave as an acid or a base, and it just depends on what it's stronger as. And so these are called amphoprotic or amphoteric anions. And these come from polyprotic acids. So acids with more than one ionizable proton still attached. An amphoprotic means it can act as an acid or a base. And it just depends on what it's stronger as, what it'll react with. So the Ka and Kb are the same species. So if we have sodium hydrogen phosphate, we form hydrogen phosphate. And hydrogen phosphate can do two things. It can remove a proton, so it acts as a weak acid, or it can gain a proton, or it acts as a weak base. So you would have to look at which one is bigger. Is the Ka of dihydrogen phosphate bigger than the Kb of phosphate? So it's Ka the Ka is bigger than Kb, it's acidic. If the Ka this is only do when it's an amphoprotic species, such as dihydrogen phosphate, hydrogen phosphate, bicarbonate, bisulfate, etc. So that's how you would determine the pH of a solution that contains an amphoprotic anion. And again, I should have put -3 here. There should be a -3 charge for phosphate. So you would do this for things like examples. If you had potassium bicarbonate, you would look at the Ka of carbonic acid, the Kb of carbonate, and see which one is it greater as, and then you can determine whether it's going to be acidic or basic. Same thing for potassium or sodium bisulfate. You would see what's the Kb of sulfate and the Ka of sulfuric acid. Which one is larger? Let's tell you whether it's going to act as an acid or a base. And then example, potassium oxalate. So it'd be HC2O4. Again, you would check, is the anion going to act as a acid or as a base. It depends on what is the stronger acid. Is it the Ka of the weak conjugate acid, or is it the Kb of the conjugate base? So this is just an overview of what we talked about. So again, for example, we talked about neutral salts containing the cation of a strong base, anion of strong acid. Acidic salts typically are going to be the cation. So there are two criteria: the cation of a weak base and the anion of a strong acid. These are going to be your protonated amines salts, or with a smally highly charged cation and an anion of a strong acid, which is your transition and post-transition metals. These are going to be acidic. For basic, it's the cation of a strong base, anion of a weak acid. Now, where it depends is when you have a cation of a weak base or small, highly, like a transition metal, and an anion of weak acid, you have to look at the Ka of the cation and Kb of the anion, which one is bigger, and that'll tell you whether it's going to be acidic or basic. If you have a cation of a strong base and an anion of a polyprotic acid, such as bisulfate, bicarbonate, you gotta look at the Ka of the anion and Kb of its cation and see which one is it stronger as. And that'll tell you whether it's going to be acidic, basic, or neutral. So here we want to know, select the three compounds that would form acidic solutions. So since we're looking for acidic solutions, we're going to be looking for cations that are either transition metals or protonated amines. That means nitrogen has 4 bonds. And we want an anion that is neutral. So what do we want? We want a cation that has a transition metal or a protonated amine and an anion that is neutral. So let's look at these. So sodium chloride, is sodium acidic or neutral? It's neutral. Is chloride acidic or neutral? It's neutral. So this wouldn't be acidic. This would be neutral. Is potassium acidic or neutral? It's neutral. Is fluoride basic or neutral? It's basic. So this solution would be basic. Is copper acidic or neutral? Well, copper is a transition metal. It's going to be acidic. Is nitrate basic or neutral? Nitrate's going to be neutral. So this solution is acidic. Because the cation is acidic, the anion is neutral. Next we have C6H5NH. That's the cation. Is it acidic or neutral? So if it's neutral, does it come from a cation of a strong base? The answer is no. This is acidic. Is chloride neutral or basic? Chloride is neutral. So this solution would be acidic. So far we have D and C. Next we have lithium carbonate. Is lithium acidic or neutral? It's neutral. Carbonate, basic or neutral? It's basic. So this would be a basic solution. Next we have ammonium perchlorate. Is ammonium acidic or neutral? it's acidic. Perchlorate, basic or neutral, it's neutral. So this would also be an acidic solution. Next we have C2H53N. Notice there is no cation or anion. This is a molecule, so this is just basic because it's an amine. And that's how you go through the thought process of determining what is acidic and what is neutral. So here we want to look at each one of these solutions and determine whether it's acidic, basic, or neutral. So first we have barium fluoride. So barium fluoride, barium is neutral. Fluoride is what? It's basic. So this is going to be basic. Iron 3 iodide. Iron is what? That's correct. It's acidic. Iodide is what? That's correct. It's neutral. So this would be an acidic solution. Lithium lithium chloride. Lithium is what? That's right. It's neutral. Chloride is basic. So this is a basic solution. Next we have potassium perchlorate. Potassium is what? It's neutral. Perchlorate, neutral. And the reason it's neutral because the anion comes from a strong acid. So this is neutral solution. Sodium chloride, we've already talked about many times. You should know this is, that's right, neutral. Sodium nitrite, sodium is neutral. Nitrite is basic. So this would be, that's correct, basic. That's how you determine whether something's going to be acidic, basic, or neutral. So another acid-base theory we want to talk about, and this is probably the more important one, is Lewis acid-base theory. Lewis acid-base theory depends on electrons. And so a base is any species that donates an electron pair to form a bond. An acid, any species that accepts an electron pair to form a bond. So it's all about electrons. And Lewis acid-base theory can explain almost anything. It can explain why hydrogen bonding occurs, why halogen bonding occurs. It explains why certain compounds react the way they do. And so the base donates its electron. So here H plus is a Lewis acid, and you have some Lewis base. It could be, for example, ammonia. So if we have ammonia, which is the Lewis base, plus H plus, the Lewis acid, what we get is the Lewis acid-base adduct, which is NH4 plus. So again, ammonia is the Lewis base. It has a lone pair of electrons it can donate. H plus is a Lewis acid, and then you have ammonium as the acid Lewis acid-base adduct. So all Bronsted-Lowry acids donate an H plus, which is the Lewis acid. So in a Bronsted-Lowry acid, what's the Lewis acid? It's H plus. The Lewis adduct is the product of this acid-base reaction. So for example, up here, ammonium is the Lewis adduct. So for a Lewis base, it has to have a lone pair of electrons to donate. So Lewis bases can be amines, are Lewis bases. These are some common, so I should say common Lewis bases. Amines, carboxylates. For example, acetate ion can be a Lewis base. What else? Anions, so like bromide, iodide, etc. Those could be Lewis bases. These all have accessible electron pairs. But don't be confused. So for example, I minus is a Lewis base. Okay? But I2 could behave as a Lewis acid. So don't be fooled that just because something is a Lewis base one time, it's always a Lewis base. If I is an anion, yeah, it's a Lewis base. But if you see I2, it could behave as a Lewis acid. It could accept a lone pair of electrons. So you got to be careful. So don't go into organic chemistry saying, well, Dr. Armand said iodine is always a Lewis base. That's not correct. Iodine is a Lewis base when it's an anion. But when it's in other forms, it could be a Lewis acid or Lewis base. It just depends. And most of the time when it's in an organic compound, it's going to behave as a Lewis acid. So these are Lewis bases. Amines are most common. Water is a Lewis base. I forgot to put water as well. Water is a Lewis base as well. And so those are examples of Lewis bases. Lewis acids have to have a vacant orbital to allow for the lone pairs of electrons. These can be electron deficient atoms. So those atoms that are deficient octets. So we're looking at things like aluminum fluoride, boron trifluoride, things like that. Those are electron deficient atoms. Again, those elements that can have a deficient octet. Polar multiple bonds, such as SO2, you put it in water, it forms an adduct, which is hydrosulfuric acid. And then, of course, metal cations. Metal cations are Lewis acids. The metal is electron poor. When you put it in water, it's electron rich, the water, so it donates a pair of electrons, and then you get your hydrated species. So these are the three main groups of Lewis acids. So we want to know which of the following could be classified as a Lewis acid. So BF3, is that a Lewis acid? So does it come from an electron deficient? Does it have an electron deficient atom? Does it have multiple polar bonds? Or is it a metal cation? And the answer is it's a deficient element. So boron is electron deficient. So it would be a Lewis acid. What about B? Is B a Lewis acid? That's correct. It is not, because it's an amine. Amines have lone pairs of electrons. What about C? Is C a Lewis acid? That's correct, because it's a transition, it's a metal cation. So this is because it's a metal cation. Metal cations are Lewis acids. Is water a Lewis acid? No, it's a Lewis base because it has an accessible electrons to donate. What about THF? This is THF here. Is it a Lewis acid or a Lewis base? And that's correct. It's a Lewis base because it has an accessible electron pair. So we want to identify the Lewis acid and the Lewis base. So obviously, if one is the acid, the other is the base. So what I'm going to do is a red box equals Lewis acid. So if I circle the red box around the species, it's going to be the Lewis acid. That means the other one is the Lewis base. So in our first example, which of the following is a Lewis acid? Is it the hydroxide or aluminum hydroxide? And that's correct. It's aluminum hydroxide because it has a deficient octet. In the next example, SO3 or H2O? We just said H2O is a Lewis base. SO3 has multiple polar bonds, so it would be a Lewis acid because if you draw the Lewis structure, it has multiple polar bonds. Number 3, we have cobalt 3 plus and ammonium. Cobalt 3 plus is a metal transition metal cation. It is a Lewis acid. Now in this one as well, we have BOH3 plus H2O. Boron is a deficient octet, so it's the Lewis acid. In number 2, we have cadmium 2 plus and iodide. Cadmium 2 plus is the Lewis acid, is the transition metal cation. And then number 3, silicon tetrafluoride and fluoride. Well, fluoride is an anion. It has an accessible lone pairs of electrons. So it is the Lewis acid here, SiC. So which are the Lewis acids, Lewis bases? Copper 2 plus is a Lewis acid. And tin 2 chloride is also a Lewis acid as well. So on that note, that concludes today's lecture on acidic, basic, neutral salt solutions and Lewis acid-base theory. There's one other small part I'm going to include as well, which is dealing with acid strength. But on that note, I hope you enjoyed today's lecture. And until next time, it's Dr. Armand signing off. Have a good day.